Okay, so that's the announcement. The message also, which is by Xiang Tang. I don't know my pronunciation. The title, the last time here, the kernel of homogeneous spaces on Bismut formula. So, thanks.
Thank you very much. I would like to start my talk by thanking organizers for the invitation, for the wonderful job organizing this conference for our friend, my co-author, Markus. So I apologize for a very technical title. I will try to explain to you what's going on in this part. I'll try to make it accessible, but to start my talk, I want to share with you a photo. So now the quiz. Marcus, where was this picture?
That's a good question. Shane, was that in Changqing at when we were at the Churn Institute? And
Yeah. You passed the quiz. Okay. This one was taken in 2017. Only what kind of culture? Cherry.
well, maybe the ship.
Yeah, you said Chinese or Sukshi. Yes.
Yeah, we're looking at the bottles.
Oh, yeah, of course. And so, alias Marcus for
2019.
Yeah, right.
I first met him. That was in Yanli, in Basel. And then we found out we both, actually Marcus and Hassel and we were independently working on something to talk about traces of Hawkshire homology of deformation quantization of orbifolds. So he immediately invited me to visit Frankfurt. So while I visited Frankfurt, they gave me this book. This is my copy. You can see, it's already old. And that's the gift he gave. So this is really a great work for me, on my research. And also this is the most cited publication of Marcus. So congratulations. Thank you. So now let's so now let's move to my talk. So my talk today is about, B groups and heat kernels. So I will explain more about this throughout the talk. So here we'll consider some Lie group and some convex subgroup and geometry on this quotient space. This is what we usually call the homogeneous space. And the object we're interested in is the one we heard a lot throughout today's lectures, the talks, is about the heat kernel. So the particular property of the heat kernel we're interested in is about the limit as t go to infinity. This last time period here. It turns out what we found is this is a classical subject in geometric analysis, index theory, and what we found is using some recent development of Jean-Michel Bismut, we are able to connect this study to some representation theory and topology of homogeneous space. That's the application. Now here is the outline, the plan of my talk. I'll try to explain to everyone. I know non-mathematicians here. I'll first explain to you
Thank you.
what we are studying. And what is also this office. So
A little bit.
and then I'll explain to you the main result of our work. So let's move to the next page. So these are my two collaborators. So the co-author on the left is Shen. He is based in Paris. And the co-author on the right is Yanli. He's my colleague at Summits. Okay. Now let's go back to the familiar object, real line and heat kernel. So I hope everyone learned this in our undergraduate classes. I want to enjoy it. So here we are interested in the real line. And then, I'm taking this advantage of the topics I've heard earlier today, we're looking at this operator we all learned from calculus class, the differentiation operator. And actually, it has a fancy name here and called the Dirac operator on the real line. So I put this imaginary number here to make it self-adjoint. So now, for today, for my talk, I will focus on the Laplace operator, the square of this Dirac operator. So this is the equation will be interesting because this goes back to the study of physics. We're interested in the heat propagation. So we are looking at heat equation with the initial condition. Right? And this equation, we know how to solve it for a long time from the, 19th century. You know, the solution to this equation can be written as an integral operator with a very nice smooth function, this smoothing kernel. I wrote down the formula, so it's essentially a Gaussian. Right? So this is the heat kernel of real line. So that's what we are interested in, the object of the real line. And we are trying to study today is to generalize, this heat kernel on homogeneous space, or some more general spaces, and the properties of. So that's said. I want to put this into more, functional analysis framework. So what we are looking at here is we are looking at some multi-dimensional linear algebra. So we have a self-adjoint operator defined by the Laplace on the L2 functions. This is an unbounded self-adjoint operator. We can look at the heat kernel. This is, this one parameter semi-group defined by this self-adjoint unbounded linear operator and satisfying the following property. Well, at T but said, have identity operator. It is a semi-group, so we have this group property, and then if the tensor generator of this semi-group is exactly our Laplace of, or the modulus of the Laplace of. So the question we are interested in here is, we are interested in computing the traces while looking at the large time behavior of these tricks. Okay, now to explain this question, let's go back to finite dimension and see what does this large time behavior tell us about our object. So for that, we're looking at a finite dimensional Gilbert space, just as 0 to Cn. Then we have a self-adjoint operator. Now we have a Hermitian matrix. And on this, that's the property of Hermitian matrix. Right now we learned from linear algebra, for Hermitian matrix, we can diagonalize it. I can have this eigenvalue eigenvectors. Now using this, we can. Let's try it. Okay, so when I write down this droplet, on each eigenvector is just exponential. This is again, when we have A as a diagonal operator, the heat kernel, the heat operator is also diagonal operator, then we can compute these trees, just adding up the entries on the diagonal. So now we're going to try to answer the question at least. What is the behavior of this trace as t go brief? Now we see that this is just a sum of exponential function. T now died. This will be dominated by the smallest eigenvalue. Right? And now, what is A? A is the non-multiplicity of the smallest eigenvalue. So, in a sense, you can see that we were asking the question to hugely dimensional word. What is the smallest eigenvalues, and then what is the multiplicity of of this eigenvalue? Now let's look at back. So that's this summary of our studying of linear algebra, four-dimensional linear algebra. Now let's move to real line. Now, this is the heat operator, heat kernel I just times 10. Now the one observation here is, unfortunately, this operator is not a trace class operator. So we will compute the usual, Hilbert-Schmidt trace. This operator is not a trace class. It's in particular, so yeah, that's the property. Now, in particular, if we look at the restriction of our hit kernel to the diagonal when we set x equal to y, well, the exponential term disappeared. We just end up with this nice expression of 1 over square root of. This is the constant function on the real line. It's not actually integrable. So the trace is not well defined. Then you heard this morning class of Pflaum, we can do something, Pflaum algebra or functional analysis. So that's what we call the L2 trace. So to do that, we need to make an observation that our real line carries the symmetry of R translation. Now using that, we can also observe that our outages, they are all invariant under the transformation. So we can define the L2 trace by basically considering the value of our heat kernel at one point or at the origin of our group, the real line as a group. So now the answer is, when we compute the L2 trace or the volume trace of the heat kernel on the real line is actually 1 over square root of 4 by t. So you can see that this answer is really an infinite dimensional phenomenon. Because just now look at matrices, we have only exponential of active lambdas. So only when we consider infinite dimensional Hilbert space, we have this kind of phenomenon. So that's the real line. To the next one, I want to move to 2 by 2 matrices. So for 2 by 2 matrices, so we have, matrices with determinant equal to 1, that's the special linear group. Now for the space we're looking at, we'll look at the compact subgroup of SL2R. So that's the special orthogonal group. So basically we consider, orthogonal matrices with determinant 1. And now we look at the portion. So this is a well-studied space in mathematics and also in physics. This is the upper half plane, carry the complex structure. So with the Mobius transformation of SL2. So here we are identifying looking at this as the upper half plane in complex plane. So Z is a complex plane. And for this section, we have a nice example of the metric, this invariant Riemannian metric. This is an example of constant curvature metric. This is actually negative, it's invariant metric. So we can repeat what we just discussed or real to this upper half plane. So we can talk about the heat equation, Laplace equation, or Laplace operator. So you can see already from this expression how Laplace will not be the usual Laplace. We have to take into consideration of those ones. So that's the Laplace operator on the upper half plane. This one is invariant with respect to the SL2R action. So this is the invariant operator. And the heat kernel for this Laplace operator was studied by Markus in the 70s, early 70s, late 90s, early 70s. So he actually computed heat cut this prism. So just now for real line, we have some power of t and then the Gaussian function. So now similarly, by Markus C, this is we're replacing the Gaussian as this integrals, still something harmonic Cauchy function and then some peak time, right? So that's Markus' formula. Now, looking at this, we can try to use this Markus formula to compute the volume matrix or L2 trace of this heat kernel. Okay, so what that means, we are looking at this function restricted to the here for the upper half space. We're looking at here rho to be 0. So now you see that, well, this function actually is integrable with this bullshit. So it's again like what do we have? We had some power of t, some half integer power by the what we saw for the r, the real line. But now the interesting new phenomenon is this a quarter of t. This suggests that our Laplace operator has a spectral gap. So this is something like the smallest eigenderivative, or smallest positive eigen p. So that's about the example of SL2R. These are upper half space. What do we have for their large time behavior of a trace? So now we can also ask about the small time behavior. That's what we usually see you at study of Wall's law. So that goes back to Wall. He observed that when we look at the small time limit, it's related to Wall. So now let's continue. So now I want to generalize the examples we have to the general homogeneous space. So please bear with me about general framework. So we're looking at GLAC, so unbounded wonderful complex value matrices. And for reductive group, I'm using like Hardaw's practical definition. So we're looking at subgroup of complex unbounded matrices. They are closed under conjugate transpose. So what between the transpose and the conjugation, our group is closed. So we still any group. And now K is a maximal compact sub beside our group. Now, maybe you look at some examples to have some familiarity with this setup. One example is we can consider G is the real line, and now we can have K is actually just treatable. And we can also, okay, so C is this one, this two. Okay, so we can consider GLNR, and then there's, general, all invariable real valued matrices and the orthogonal matrix. That's a possible pair of G and K you can consider. And the other one is the one we just saw and considers special linear group. A matrix is with determinant 1, and that's special orthogonal group. Okay. But then we can also have simplicity version or your other generalizations. So all this fits into this kind of framework. So here to look at the space, our space will be the quotient. Space is the coset of the bigger group by the subgroup. So this is the nice, manifold bracket theory. So G is a Lie group, is a manifold. K is a subgroup. The quotient is again a smooth manifold. Now, if it carries a G action, so G is a Lie group, so the smooth action. Now, because our K is compact, this action actually is prime. That's the framework we have heard this morning in Kessel's talk. So, for my talk, I will not assume you understand the Dirac operator spinors. So let's just take it easy. We will assume that we have a representation of our compact. Okay, so we started with a representation. Well, the representation of K on some, Commission vector space E, the unitary representation. And using this data, we can consider the bundle. This is now, we take a product of G together with the E. So K will X from G from the right. Remember I took the right cosets. and also kx on E through the representation. So we have taken the quotient. This is now a nice Hermitian vector bundle over the manifold X. And that's the vector bundle over X we are looking at. Okay? And this bundle, because of its G, actually carries a natural G-equivalent bundle structure. So this carries a natural connection.
Can we see that this is not a trivial bundle?
So this, in general, is not a trivial bundle because of the existence of K. Because K, X both are both factors. The quotient is not a tree. That's a very good question. Thank you. Any other questions about the set? So one special case, if I just consider this to be a trivial representation on the complex line, the one-dimensional complex space, then I would just consider G bar K a trivial. That's a trivial bound because the representation is trivial. But in general, the representation is not trivial to the boundaries. Okay, well, with boundaries plotting head, I can move on. Okay, now let's go. So I need some infinitesimal geometry. So here we have, the B algebra of our group G, and K our B algebra. So we are the infinitesimal object we need to associate with our global group. Now, the nice thing of working with this class of reductive group is we have a nice canonical binding form on this ERGH. This is usually called the K form. Okay, so this is the non-T-channel, the bilinear form. And we'll use that to define a metric. So here, this binomial form actually is K invariant. Okay, so using that, so remember we have K is a subgroup of G. So inside the B algebra G, we have a subspace K. So using this bilinear form, we can decompose our vector space into a direct sum of two subspaces. One is the P, the other is K. P is usually referred to typologic. Let's start about this terminology. Okay, and because our B, this bilinear form, is K invariant, we can make this representation, decomposition actually K invariant. So P also carries an interesting non-trivial K representation. So that's the setup we have. So Kx on the P. For now, remember just now I had a K representation. I filled a vector bundle over G bar K. So now I have this nice K representation on P. We can build a vector bundle over G bar K. So what is this bundle? This bundle actually is the tangent bundle of the homogeneous space. So now, to remind you, we have this G action on G side, although we can use the G action to act on the whole bundle. So we can look at the corresponding infinitesimal action of the Lie algebra on this bundle. So this is they give us a nice differential operator. So we are here, I'm trying to write down this operator explicitly. To do that, I'm using a basis of P and also a basis of K. You can see that P has m dimension, K has n dimension. Now the operator what interesting is this operator. So this is usually referred to as a Casimir operator for the Lie algebra G. So this is related to the Laplace operator on G mod K with the coefficient f is almost the Laplace operator, we can see, but up to some constant. This is usually called the Casimir operator associated to the compact group K, but because here, while quotient of K, this one is just a constant. So you can see that the Casimir G is essentially the operator. Oh, yeah. So that's what I explained here. So if we look at the space of sections on X for the bundle F, right, this can be identified with the space of K invariant sections, K random functions actually with the value in E. Now this Casimir G is actually a second order differential operator. This is up to a constant equal to the Laplace operator we started with on this G mod K up to a constant. So what Bismut did was in the last 20 years-ish, he developed a very powerful method with referred to using some hypoelliptic Laplacian. So this is not an elliptic operator we heard today in Hassel's talk. No, these are not elliptic, but actually hypoelliptic, using some more general theory of Homander. And then he was able to find a extremely nice integral formula for the heat trace of this operator. So basically, you can say is the heat trace of the Vogan Laplacian on manifold X. So I don't have time to explain to you how Bismut did it, but here is a kind of a very brief cartoon idea of the course. So he Bismut put this into finally. So this operator L is some operator actually not just on X, actually on some Beadle space. So this is an operator on X, actually tangent upon of X. This is a hyperelliptic operator parameterized by the B. And then he considered some kind of a supertrix. So here you can see in our study so far, we don't have a graded bundle. It's just for one bundle, one trace, like a Euro trace. But he needs to introduce this super trace. Now, with that super trace, he can prove that super trace of this, semi-group of this hypoelliptic Laplacian actually is like what we heard this morning. Like the heat kernel of the super trace of the Dirac operator is independent of this parameter. So there will be the super trace. And then with this in mind, we can take the limits, like what do we do for heat kernel trace? We take B go to infinity, B go to 0, right? So you will classical case when we do that, we have the beautiful Atiyah single index formula. But now with this hypoelliptic Laplacian, what Bismut achieved was when we let B the limit to infinity, we get to the L2 trace. The kind of spectral side. Now, if we go to this limit B equal to 0, we get to something infinitesimal. And now this is actually there's some integral formula I'll explain to you in a moment on the dual of the Lie algebra. So, just a remark. So here, if we are looking at the general vector bundle, that's why this computation is interesting and difficult. Because in general, this trace is a function of t. It does change respect to t. So Bismut formula gave us the formula for all t. So this is kind of different from with the Euro index theory, where we consider super trace. So for example, if we put here F to be the spinner, either what Hassel discussed this morning, or the kind of twisted spinner bundles, then there, this trace is independent of it. So that's making the computation much more robotic. Now, the powerful machinery Bismut developed is he's still able to compute the short time limit for p equal to 0, and that's come to his formula, which I'll explain now. So this formula starts with something we all have seen this one. This have a kind of this state head function. So this is a function on the real line. You can see the hyperbolic stage function here and x. Now what we will do is we'll put Covariance matrix into this variable x. It's here because, Hermitian matrix, we can diagonalize it. So this is always well defined. Furthermore, because this atomic proof is always positive, so we take the square root. So this they had variable on matrix is well defined, and it produces as a member. And the Bismut formula is an integral formula of using this function and integral over the Lie algebra K. But this is really using the testable formula, but now this formula you can see it depends on T in general. This is also the reason providing us more information than the Euro defect scale. Is now maybe in the next slide I'll explain to you what are these concepts. So any questions before I move forward?
So, year was this? What year?
What year was its formula? This was about 15 years ago. Yeah, so maybe for our physicists, so Bismut learned that his haploidentical Laplacian, this operator is inspired from the Dirac operator on the loop space. Of course, there, mathematics, there's always a lot of issue with that, right? So I think Markus, Henry all have no interest on that. So what the Bismut did was, well, he is able to do some truncation, and then establish this operator on a 5-dimensional manifold, and make this operator well defined, and then give us a wide mathematical formula.
Same analogy with then.
Right, same analogy, but now for the general vector bound, not for the kind of Dirac, the spinor bound. So yeah, I should remark, in the case what we have this as is a spinor bundle of twisted spinor bundle. The trace formula goes back to Henry's work with Alan on the L2 index bubler. And there, this trace formula with T goes to infinity, we really get some representative information. That's the discrete series representation. And those vectors that I counted the work of Attila Schmidt is the formal degree of the discrete series representation for a linear G. So now the kind of new contribution here is this computation now works for anybody. So there's no need for a spinor bound. So here this trace is just with the standard out trace. But this makes this work like as distinction. And so as Hassel mentioned, so with Markus, we are able to generalize this to cocycles, following the idea of Henry and Aleka, Jordan. So now let me explain to you a bit more about this formula. So here, we're writing on Y0K, this is the D algebra element in this D algebra. So first, Bismut, instead of consider the D algebra K, he want to think about some polarizations, like the first talk he presented this morning. But he deliberately put this idea, because he want to think of this as from some complex polarization. Or you can see this some kind of KD transform. And now for this algebra element, our K, as we mentioned, we can look at the algebra representation of the Lie algebra K on G, and this G we had the natural. So this CG we just saw was some constant associated to the Casimir operator, and the algebra representation split into a properwise diagonal operator with respect to this decomposition of G mu to P and K. So in this way, we have two components. Now, let's me. So yeah, so maybe go just one comment about this formula. You can see that in Bismut formula, he distinguished the k part is in the denominator. For the p part, it's in the numerator. So this part is the representation theory information, and this part is the Gaussian. Now, as I will show you this, let's go to look at the example of SL2R. So now for SL2R, we can consider this weight. This one is associated to the representation of the circle. We know for representation of the circle is all parameterized by the Yanli number. So just the natural number number we can associate to this irreducible representation of SL2. Now, this Bismut formula reduced to this one, the one we saw in McKean's formula. You can see here this A-hand function, this exponential power, and now here, this is the heat kernel. Now we have this shift determined by the law. So that's the Bismut formula for this upper half space with this bundle is general coefficient. So now let's see the last time to hit. That's the part of the title of my talk. We want to take the name as t go to infinity, right? So as t go to infinity, you can look at the formula here. You can see, this part can be combined with this. Then you can do some calculus type of computation that will reach to the following conclusion. So if lambda is greater than or equal to 2, the absolute value, we get to something like this. Just exponential term. So this is like the 5-dimension case. So if we are familiar with the equation theory, this is reached with space series representation. For the SL2R, we have discrete series representation. So for lambda equal to 1, that's the length of spherical placement representation. For the other one we see, we have no exponential term because we know for those representations, we don't have spectral gap. For we don't have this exponential term, but we have this one. So what does this tell us? This column tells us what is our operator does not have spectral gap, but we can ask the distribution of the spectrum nearby 0. How dense is it? That's this power does. So this is relating to the so-called Markov-Schulin. Yes, please.
In case 1, is there a missing minus sign in front of the exponential, or am I misunderstanding what IT is?
So sorry, yeah, I should have a minus sign here. I forgot. So
Okay, thank you.
And then for lambda equal to 0, this is really the one we saw in the McKean's formula for the classical but on the last orbit, it has limited to a dome. So we have as a power. So now one line explanation of the curve. I guess when we have this kind of integral, our physicist friends know how to do it, right? With stationary phase, or do some local expansion. So basically, that's the idea. Because here, this is the Gaussian with functions, rational functions with very nice controls. And then do that, that's the kind of the computation. Okay. Okay, so now go back to the general case. The general case, this is the answer. So the L2 trace of the heat kernel of the heat operator associated to Casimir operator has the following expression. It's some constant, some polynomial power of t, and then the spectral gap gamma t. So alpha is a positive number, real number. I'll show you what is the local height. Beta is some negative half integer, and then gamma is a real number. So here is one case we know beta is 0. So I have to apologize, I'm using the representation theoretical terminology here. So when G and K have the same complex rank, so you can think about the example of SL2R. Right? In that case, actually you see that we know beta is 0 and when this tau representation is regular, we need this to make sure. That's the case when we had SL2R when lambda was greater than or equal to 2, when we had the discrete series representations. For those, is beta is appear only the exponential. And in that case, basically we are saying that our operation has a spectral gas. So just starting with the smallest eigenvalue, and the next one, has at least a gap there. So this calls us the gap property for a process. So, almost done. Thank you. So I'll finish soon. I don't have much time, but a lot of. Yeah. So now let me explain to you a bit more about the hazard. Then I will call it for my talk. So here, as I mentioned, when G and K have the same rank, the tau U is regular, or beta is 0, and in this case, alpha, the number alpha is what Henry and Alan Kang compute the formal degree of the reducible representation associated to the discrete series representation of G. So, what is alpha? So alpha actually also has a very nice, connection to, I guess, to physics and also to Lie theory, to integrable system. It's a generalization of this form, the McDonald and meta-McDonald integrals. So you can see this one was already in Bismut formative, so it's natural to expect this. And this one shows up when we look at the expressions of a hyperbolic sine function. Only this poem shows up in the link down. So that's this, is alpha. But this is in a wise case, in this regular case, but in the, in the kind of degenerate cases where they say when tau is not gradular, then this integral actually become more and more. So it's a generalization, as what I said here, it's a generalization of the classical meta-McDonald form. So now, I have explained to you the alpha, the beta. Now I will try to explain gamma. The gamma was in the exponential of the gamma t part, right? So to explain that, I have use some Lie theory information. So we have to use rho G and rho K. They are the longest positive root for associated to root system on G and K. And now, what do we observe? What do we compute it was to identify gamma? What do we look at this expression? So lambda is the weight of our Lie algebra. So when you look at this shift, and then the projection of this shift to the wall chapters. So why do we need this? So we need this because, okay, so in our Bismut formula, here is a heat column. Here had a heat column Q and the matter X K squared. But he also have the trace of lambda. So we need to combine this together to look at the large T limit. So because of that, we need to have this shift and the projection. Now the formula of gamma was of this. It turns out this one is an important quantity in representation the E theory. This is appearing in Vogan's theory of his lambda map. In his classification of unitary representations of reductive books. So in this way, we can see a kind of a very interesting and deep connection of the representations. On one side, we know the representation theory, the Hashchandra's formula appeared when we study L2 of Gma K. But on the other side, when we compute the last time behavior of the heat operator, we get to see another story of representation theory of the more easily testable the combinatorial Lie theory examination.
6.2 and also the express.
Yeah, so this was a Casimir you can express this. Okay. So I will stop here and we will
Sounds collateral. That's it. So, questions, problems? Yeah.
To what extent is it important that the group G is GLM?
also we need the group to be well.
For example, would it work for the meta-state electric?
Unfortunately, we need this to be Hashchandra class. So I don't think it's included the multiplet. Unfortunately.
Okay.
Yes,
When making us going to the formula,
right.
it's so good. I think it was related to his work on using plus standard text for juice or the portion the hyperbolic manifold usage. But I come out not the commodity. So I think this probably should cut also gamma when gamma at this pizza.
Yes, this works for in the same way. Is that no? So the heat trace between them and
Not to compact finite ball.
for fire volume, this could be tricky. Yeah. Well, actually, what I think about it is, for fire co-volume level, because even there, we need to worry about, the spectral count. I believe.
Well, that's where the many back is.
Right. Of course, we should use neighbor on the. Thank you, Tom.
Is there some meaning to capital N, which was the power and the exponent? Is it multiplicity of zero-mont resonances or something like this? Are you onto
So you had the gamma, the
Yes.
gamma.
Well,
Beta, sorry.
or beta. Yeah,
Beta.
beta is the so-called logical Verschuebung event for a manifold. Yeah, so this is some kind of spectral event, but it's a topological event.
The related analytic picture.
Yes, it's about the secondary invariant. It's kind of dependent on smooth structure. So that's this beta.
And can that theta be fractional or not or any or because it's not like
But this is beta just seems half improvized. Yeah, I don't know if was
can you escape that?
before that we can I think to the singular computation, then we will have some rational number bias, right? Yeah. So by the way, we can also identify the space in the homogeneous space case. So the past computation for the Vogan Verschuebung values was using classical Hashchandra theorem. And for this one, we can actually give a kind of a quicker, more direct computation of it.
You mentioned it has to do with density of eigenvalues close to the edge of the spectrum.
Right. Yes.
What do you mean by density?
So you can look at the spectral measure and compute the volume trace of the spectral measure. That's basically what it is.
The generalization of the counting.
Right. Is that? So I've kind of put everything under the rug. Follow your suggestion.
So what all the spectrum of this CG Vogan?
Oh, so this one, in general, you could have spectral gap. So that's a very continuous spectral. Would I have a equilibrium spectral too?
So when you say skypal gap, it means the first it has an item there.
Right, gap is 0 and a jump.
Status starts at gamma, yes. Status starts at gamma. Is it constant discrete or is it infinite degenerative this gamma or?
Well, so if beta is there, then it's infinite, it's 1. No, if it's continuous spectrum,
Yeah.
then, the beta tells us the information of. If beta is positive, then this cell tells us there's a spectral gap.
So the degeneracy of the first level is non-homogeneous level.
Well, it's so the degeneracy is determined by the information of the representation B. So it's not always degenerate, depending on basically where this representation is located, the highest weight. If it's kind of in the middle of the wall chamber, so it's kind of more stable, then we won't have spectral gap. But if we are in the kind of nearby the walls, so basically saying that we could have some void perturbate, we could cross the walls. Then do have degeneracy. Then the gap will disappear. Now we can, this power will tell us all the spectral, the best.
So we should make a bond compassion that, as physicists, we always, all the text will always stop at compact for representations for the, say, here all the discussion was of non-bond. We are kind of highly really false.
We have a word expert.
Some question, Mark, solution? Yeah. So thanks a lot for your very last thank you.